These are your notes on partial pressure. So partial pressure is the pressure of each gas in a mixture. And Dalton's law of partial pressure is the total pressure of a mixture of gases. So that equals the sum of the partial pressures of all the gases that make up the mixture. So if we're looking at an equation for partial pressure and total pressure, we would say total pressure is equal to P1 plus P2 plus P3, so on and so forth. We'll leave that blank space for just a second as we have an example to draw. So if I'm looking at my first problem, it says H2 has a pressure of 100 millimeters of mercury and carbon dioxide is 200 millimeters of mercury and nitrogen is 50. What's the total pressure? If I know my partial pressure equation is pressure total equals the pressure of 1 plus the pressure of 2 plus the pressure of 3, we could also say that the pressure total is equal to the pressure of the hydrogen plus the pressure of the carbon dioxide plus the pressure of the nitrogen. So in this case, we can simply add them up, and that would equal the total pressure of the system, which is 350 millimeters of mercury. So a container that has a total pressure of 800 millimeters of mercury, and we know that inside are two gases, A and B. So if gas A has a pressure of 620 millimeters of mercury, what is the pressure of gas B? So we know that pressure total is equal to the pressure of A plus the pressure of B. So I would say that pressure total is equal to 800, and I know that pressure A is 620 plus the pressure of B, so I'm going to do some simple algebra there, simple math, and figure out the pressure of B is 180 millimeters of mercury. So why do we need to talk about partial pressure? How does this apply to the gas law unit that we're dealing with? We always generally collect in our labs gas via water displacement, and so we've done it one time in the making water lab, and we'll do it again when we do our molar volume of a gas lab. So gas collected by water displacement is not just pure gas. It's always actually mixed with water vapor. And the reason why it's always mixed with water vapor is that when you pass a gas through water, it actually excites some of those water molecules, and they are able to enter the vapor phase. So to determine the partial pressure of what we call the dry gas, we need to make sure that we substitute out or subtract out the pressure of the water vapor. So the pressure of the dry gas is equal to the pressure total minus the pressure of the water vapor. So the vapor pressure with water actually varies with temperature. So you have a chart that you've been given, and it's the water vapor pressure table. So I want you to find that chart, and I want you to find the pressure of water at 10 degrees Celsius. So I'll give you a second. Alright, hopefully you found your chart, the water vapor pressure table. So the pressure of water at 10 degrees Celsius is, I have a drawing, I forgot. So this is just a reminder with our collected hydrogen through water, okay, some of the water molecules are actually excited and become vapor and are floating around in here. So we just need to make sure if we're doing gas calculations, we would want to equate for that water vapor pressure as well. And so to get the best calculations available, we would need to subtract out the water vapor. So again, I said that it deals with temperature, so at 10 degrees Celsius, our temperature would be water vapor pressure at 10 degrees Celsius. Our vapor pressure would be 9.2 millimeters of mercury. So now find 24 degrees Celsius. So 24 degrees Celsius is 22.4 millimeters of mercury. At 30 degrees Celsius, it would be 31.8 millimeters of mercury. And at 45 degrees Celsius, it's not necessarily showing you on your chart. It shows you 40 and 50, so just take the water vapor pressure at both of those and average it, and divide by 2. So when you do that, hopefully you got 73.9 millimeters of mercury. So let's look at number 6. Number 6 says what would be the partial pressure of oxygen gas collected over water at 20 degrees Celsius and 720 torr pressure. So if I remember that my pressure of my dry gas is equal to the pressure total minus the water vapor pressure, I can say that my pressure total here in my problem, it tells me is 720 torr, and my pressure in my water vapor is 17.5 millimeters of mercury. So when I do that subtraction, it's just 702.5 torr. So that's my dry gas pressure. Okay, I'm going to do one more example problem with you. I'm going to look at number 7. So it says a 3-liter sample of oxygen gas was collected over water at 23 degrees Celsius and 725 millimeters of mercury pressure. first thing that you want to do in this problem is find the pressure of water at this temperature. So we want to find the pressure of the dry gas and the temperature of the water. So the pressure of the water, when you look at your water vapor table, at 23 degrees Celsius would be 21.1 millimeters of mercury. So then the first thing that you need to do is find the pressure of the dry gas. So we know that the pressure of the dry gas is equal to pressure total minus the pressure of the water vapor. My pressure total is 725 millimeters of mercury, and my water vapor pressure, which is what I just found by looking at my table, is 21.1 millimeters of mercury. So if I subtract those, I know that my dry gas pressure is 703.9. So then the next question asks, what is the volume of dry gas at STP? And it tells me to use the combined gas law. So I'm going to set up my variables for the combined gas law to start with. So P1, V1, T1 on one side, P2, V2, T2 on the other side. So I'm going to include at STP, I'm going to say that my P2, V2, and T2 are the ones at STP. So I'm going to say P2 is 760 millimeters of mercury, and I'm choosing that unit because my millimeters of mercury unit to start with over here, so I don't need to do any conversions. V2 is what I'm trying to find, and T2 at STP, we know, is 273 Kelvin. So P1 now, this one is where people make a mistake, so please note, P1 of the dry gas is 703.9. So please watch that. So the pressure of the dry gas, don't make the mistake of putting in 725 millimeters of mercury pressure. V1 is the volume, and so we know that that's 0.3, and we got that right from our problem right here, so 0.3 liter sample. And then T1 we know is our temperature, so 23 degrees Celsius. We know we're never going to do calculations in Celsius, so we add 273, and that gets us 296 Kelvin. So then I set up my variables, P1, V1, T2 equals P2, V2, T1, and I plug in my values, and I'm able to solve for V2. So my volume at STP of the dry gas should be 0.256 liters. Okay, those are your notes for partial pressure. You're going to turn your paper over and do the notes for mole fractions, but we will practice 8 and 9 together in class.